spirited seminar series. So our today's guest speaker is Professor John Draisma. He is from University of Bern, and he has another affiliation with Eindhoven, TU Eindhoven, and he will be going to discuss about infinite dimensional geometry with symmetry. So here you go, Professor Draisma.
Okay, many thanks. Many thanks for the invitation to this seminar. It's a pleasure for me to speak here. Even if it is only virtually like this, I guess we're all slowly, on the one hand, getting used to speaking into the camera of our laptops now, but also maybe it's getting, well, let's say, it would be nice to have some talks in front of real people. Also, there was an issue with the time. We introduced summertime this weekend, and as a consequence, I thought that the talk was going to start an hour ago, but luckily everything worked out well now. Okay, so the topic of my talk is infinite dimensional algebraic geometry with symmetry, and the idea here is that very often in applications, some problems can be modeled using systems of polynomial equations in many variables, and then once you understand such a system, such a problem, then you typically want to increase the dimension by 1 or by 10 or by 100, and you face a similar problem, which, however, is more complicated than the previous one. In a sense, it contains the previous problem as a sub-problem. Now, a recent insight is that you can often view all of these problems in one common infinite dimensional setting. And this is especially fruitful if each of these finite dimensional problems has a lot of symmetry. The more symmetry, the better, because then you can use this symmetry to capture this infinite dimensional structure that you're thinking about in finite terms. In finite terms, for instance, on a computer, and you can actually do actual computer calculations with them. So the goal of my talk is to give you an idea about the algebra in this area that has been developed over the last years, maybe the last decade or so, and to give you several examples in algebraic statistics and tensor decomposition and algebraic combinatorics where this algebra has been used in the past. If there are any questions, please just interrupt me and speak up. I will also make sure to stop at one or two points in time during the talk to explicitly ask for questions. Okay, so here we go. Here's a very short recap of what, from my perspective, finite dimensional algebraic geometry is about. So at its most basic level, this studies algebraic varieties in C to the n, which are subsets that are defined by polynomial equations. F1 of x1 through xn is equal to 0, and f2 of x1 through xn is equal to 0, and so on. Yeah, so of course, things like a parabola in the plane is a typical example of an algebraic variety. Now, a fundamental result due to Hilbert says that you don't need to write down infinitely many equations. So finitely many of these equations suffice, and more precisely, the ideal generated by f1, f2, and so on, in this polynomial ring of polynomials in the variables x1 through xn with complex coefficients is in fact generated by finitely many of these polynomials. And what that means explicitly is that all fi for I greater than or equal to some number n are, or let's say strictly greater than some number n, are already polynomial linear combinations of f1 through fn. Okay, and now Hilbert's basis theorem was made effective in a sense by an algorithm due to Buchberger in 1965, which computes convenient bases for such ideals generated by a finite number of polynomials in a polynomial ring. And you should think of Buchberger's algorithm as a kind of least common multiple of the algorithm for computing the GCD of two univariate polynomials in a single variable. And on the other hand, Gaussian elimination for solving systems of linear equations. And the Gröbner basis you can think of as a kind of row echelon, what's it called? A row reduced form of a system of linear equations. It's more complicated than that, but roughly that's what it is. And you can use Gröbner basis and Buchberger's algorithm for a very common task in applied algebraic geometry, namely implicitization. So here you are given a polynomial map, which I'll call G, which is a map from C to the N into C to the M. And it's given by its coordinate functions, G1 up to Gm. And each of these coordinate functions is a polynomial in the N variables on C to the N. And now the task is to find all polynomials in M variables. Maybe those variables are called y1 up to ym, whereas the original variables were called x1 up to xn. To find all polynomials in the y variables which vanish identically on the image of this map. So this is also very similar to a type of task that we know from high school, where you are given, for instance, a parameterization of a line in 3 space, and you are asked to find all the polynomials in x, y, and z that vanish on this line, or at least 2 independent linear polynomials that vanish on this line, so that they define the line by means of an implicit equation. So that's called implicitization. And you can do this with Buchberger's algorithm. Now, it turns out that the image of such a polynomial map is not always given by polynomial equations only. So there's a famous theorem due to Chevalier that says that the image of such a polynomial map is in general a constructible subset of C to the N, which means that it is a finite union of sets where each
sorry, do you mind scrolling your screen up a bit? We can't see the statement of the theorem.
You can't see the statement of the theorem. That's very weird, because and on my slide, on my...
She meant just the last line, couldn't she?
That is very
yeah, just the last line.
The last line is missing. That's very strange, because because on my shared screen, I do see it. Okay, let me see if is it better like this? No, right? Because then you can, oh, this is very annoying. Okay, you know what? Maybe, let me see.
Yeah, you could just read it out. That's okay.
Yeah, so it's very strange, because I do see it on my shared screen over here, but you don't.
It is visible, and that's theorem and Z. There's one. The image of G is constructible. That's all.
That's all. Yes, exactly. Yeah, so there's nothing more after the point after HK is non-zero. So all of it is visible then? Do I understand that correctly?
Okay.
Yes, it is visible.
Okay,
Yes, it is okay.
Yeah, sorry. So this is all. Sorry if I made the impression that there was more. So the theorem just says that it is constructible, and this means that you can write it as a finite union of sets, each of which you can describe by equations and disequations. So an equation is setting some polynomial equal to 0, and a disequation is setting requiring that some polynomial is non-zero. Okay, so this is all I want to say about finite-dimensional algebraic geometry. Now let's move on into the infinite-dimensional world. So in infinite-dimensional algebraic geometry, we study algebraic varieties in C to the N, but now this N is not a finite number, but it is the natural numbers. And it is algebraic variety, and there is still something that's defined by not by finitely many, by polynomial equations. F1 of x1 through xn1 is equal to 0, and f2 of x1 through xn2 is equal to 0, and so on. So what this means, so the main difference with the previous setting is that now the number of variables that appears in these equations may vary with the equation. So you might have the first 10 variables in the first equation, and then, for instance, the next 20 variables in the next equation, and so on. And these ni can tend to infinity when I goes to infinity. Now, of course, there's no analog directly of Hilbert's theorem, because there are systems of equations in countably many variables that just need countably many equations. Like, for instance, this system here that represents the origin in c to the n is given by the equations x1 is 0, x2 is 0, and so on. And you cannot leave out any of these equations because you would no longer be describing only the origin. So now you may need infinitely many f. But suppose now that we were interested in an algebraic variety in c to the n, of which we already knew that it was preserved under all possible coordinate permutations. Yeah, if you have such a variety in c to the n that is preserved under all possible coordinate permutations, then also permutations to the equations. So you could argue that if I then give you one of these equations, you already know that its entire orbit under permuting variables must also be in the ideal defining the variety. And then it turns out that again, finitely many equations suffice in the following sets. So if you're given any system of equations, f1 is 0, f2 is 0, and so on, then from some capital N on, and you see there's the same capital N here. Let me just, there's the same capital N here that I had in the previous slide. From some capital N on, all the later polynomials are in fact obtained from the first n polynomials fj, f1 up to f capital N, by the following operations. You may apply to fj a permutation where the permutations act like this. Maybe I should have said that pi of xi is just equal to x of pi I. And so you may apply a permutation and then multiply with a polynomial in these variables. And then you might take the same fj and apply a different permutation and multiply with a different polynomial, and so on, and take sums of such expressions. And so the theorem, which was first proved by Daniel Cohen in 1967 and then rediscovered by Aschenbrenner and Hiller in 2007, says that from some point on, all of these FIs are obtained from the previous ones, from the first n ones by these operations. Yeah, so in other words, a subvariety of c to the n, capital N, natural numbers, that is preserved under all coordinate permutations can be described by finitely many orbits of polynomial equations in those variables where the orbits are taken under the infinite symmetric group. Okay. So now there turns out to be, in this case, there turns out to be a complete classification of such varieties in C to the N that are stable under all coordinate permutations. And it must be said it's quite a restrictive class of varieties. Roughly speaking, one can show that, or Nakpal and Snowden show that if you have a proper subvariety of C to the capital N, so not the entire space, which is defined by polynomial equations and stable under the symmetric group, then automatically every point in such a subvariety must have only finitely many distinct coordinates. And that means that, so you can imagine that you get a partition of the natural numbers into finitely many parts, at least one of which is going to be infinite because the natural numbers is an infinite set. And those parts are the places where you see the same coordinate. And so this classification is some sort of combinatorial classification involving finite parts. I don't want to go into the precise details, but the other, it's a very nice result, but there are very few of these sub-varieties, and in particular, they're not very useful for any kind of applications. So this is a nice result, and also this theorem by Cohen and Aschenbrenner and Hiller is very nice, but it doesn't help us much in applied algebra and geometry. Okay, so the real question is, halves of this Hilbert's theorem, Buchberger's theorem, and Chevalet's theorem for other groups G instead of the symmetric group on the natural numbers that act on polynomial rings in countably infinitely many variables. I'll restrict my attention all the time to only countably many variables. Okay, so is the question so far clear? Okay, if no one objects.
Yes, it's clear.
Yes, we are clear about it. Yes.
Okay, great. Then let me continue. So let me say a little bit about the type of spaces that I want to think about. So what would be useful for applications is if we can say something about vectors. That's basically the type of space we had on the previous slide. So vectors are tuples x1, x2, x3, and so on in C to the n. But we will also be interested in matrices, which are, of course, as you know, two-dimensional arrays of numbers, and they are in C to the natural numbers times natural numbers. And we're also interested in tensors, say three-way tensors, which are three-dimensional arrays of numbers and live in C to the n times n times n, and so on. So these are the type of spaces we're interested in. And now let's look at the groups. Yeah, first of all, we might also be interested in having not just one vector or one tensor or so, but we might be interested where we allow multiplicities, like for instance, the space of 4 vectors and two three-dimensional tensors, like this space that I wrote over here. Now, the symmetries that I'll restrict my attention to today are the symmetric group of the natural numbers. This acts by, well, as we've seen on the previous slide, it acts by permuting indices. And well, if you take only one copy of this symmetric group, then we're going to understand that it acts on all the indices, so to say. So that for vectors, that is just the action that we had on the previous slide. But for instance, for matrices, that action would be something like this. So pi of xij is x by I pi j. But of course, you could consider more difficult, or in a sense, easier situations where you have two independent permutations, one for the row index and one for the column index. Okay, so we'll think of this type of groups, the symmetric group on the natural numbers, but we will also think, and in fact, we'll be able to prove a lot more when there's more symmetry. Remember, I said the more symmetry, the better. And only permuting, say, rows and columns in a matrix or slices in a three-dimensional tensor is quite a small symmetry group, and that's the only thing that this symmetric group allows us. But we will also allow the infinite general linear group to act, and so you should think of this like this: that well, you know, on a matrix you can do row operations and you can do column operations, but on a three-dimensional tensor you can do operations in slices like this, which means, for instance, you replace the first front slice by a linear combination of all the slices behind it, or you can do slice operations like this, that you take the first top slice and you replace it by slices below it, and then there's also slice operations like this. And all of those are described by acting with the infinite general linear group on this space of tensors. And very specifically, I say infinite general linear group, but every single element of this group is actually just given by a finite invertible matrix G, and then you act with the identity on all the other variables. So all these elements are just kind of finitary operations. Okay, so these are the groups that will be acting, and now the question is, when can we have things like Hilbert's basis theorem, but also this theorem of Chevalley, and also this Buchberger algorithm. Okay, so now the rest of the talk is divided into two parts. The first part consists of finitely many vectors under sim n, and the second part concerns this group GLN, so this much bigger symmetry group. So in this first part, we study the action of the symmetric group on k row vectors, and you can also think of this as that it acts on the space of k by infinite matrices via column permutations. And so that's sort of the geometric setting, and the algebraic setting is that this symmetric group acts on the polynomial ring in variables xij, where I runs through the numbers 1 up to k and j runs through the natural numbers. And the action of a permutation is only on the second index. So the I remains fixed, but the action is only on the second index. So let me immediately give you the first main result in this area, which is a theorem proved by the same Daniel Cohen 20 years later, interestingly, and rediscovered by Hiller and Sullivan in 2009, which says that, which is really a precise analog of Hilbert's basis theorem. So suppose that you take any ideal in this polynomial ring over here, and suppose that that ideal is stable under the symmetric group via this action, then in fact that ideal is generated by finitely many polynomials, or rather by finitely many orbits under the symmetric group of polynomials. So that's what this theorem says. So that's really a very, very precise analog of Hilbert's basis theorem. And in fact, it turns out the way they proved this, both Daniel Cohen and Hiller and Sullivan many years later, is that they show that such ideals have a kind of finite Gröbner basis. I don't want to go into the details there, but it is essentially not only do they show that such ideals are generated by finitely many sim n orbits, but in fact they have finite Gröbner bases, and there's a computational machinery behind it that maybe I'll mention at some point also. Now,
Jan, I wanted to ask a small question. Is it the same Cohen who's a logician, or is it some other Cohen?
That's a good. This is Daniel Cohen. I'm not quite sure. So the reason why he was interested in this area, I don't think it is strictly a logician, but he was interested in universal.
I think he's somehow confusing Paul Cohen with Daniel Cohen.
Paul Cohen is a different man.
Yes.
It's a Daniel Cohen.
It's a different
So what was the context that he was working in?
Yeah, thanks for the question. Yeah, so Daniel Cohen was interested in, well, let's say in 1967, he was interested in universal algebra. So he was interested in varieties of algebraic structures in the sense of Birkhoff. And so in particular, he used his theorem back then to prove that every variety of two-step nilpotent groups can be defined by finitely many equations up to symmetry. So it's a kind of logic also. I mean, it's universal algebra, which I think is very close to
Whitehead and so on,
Okay. Okay, so I wanted to say a little bit about why Hiller and Sullivan wanted this result. And so let me describe this. So this is an application to algebraic statistics, and it concerns so-called hierarchical models, which is a type of family of probability distributions that I'll try to describe to you. So imagine you start with a simplicial complex of which the vertices are labeled 1 up to d. And now you assign to every vertex a random variable called xi, and that random variable can take values in the set 1 up to ni. Yeah. So then this tuple of d random variables can take values in n1 times n2 and so on up to nd. And now a probability distribution you can think of as a point in c to the n1 times n2 and so on. And let me explain how these probability distributions come about. So here's a very small simplicial complex with 4 vertices and 1, 2, 3, 4, 5 edges and 1 triangle. And in this particular case, the probability of observing I for x1 and j for x2 and k for x3 and l for x4 is proportional to aij times bik times cjkl. And I hope you realize that there's a color coding here that says, for instance, this green guy over here corresponds to this triangle over here. And this red guy corresponds to this edge, and the blue guy corresponds to this edge over here. So that's the color coding. So it's straightforward to see how this extends to general simplicial complexes.
Is it possible I ask something?
Yeah, of course.
Yeah, yes. I was wondering that by the name of the theorem, the independent set theorem, how is this relevant to independent sets in graphs, or is it not? Maybe I'm just confusing something.
Yeah. I'll mention independent sets in this simplicial complex in a moment.
Okay, thank you.
Yeah, thanks. It'll come. So now, when you do this definition, then in algebraic statistics, one is interested in the algebraic relations among these probabilities. And so let me give you one of these relations. So for instance, if you fix I and I prime, j, k, and L prime, then I get in a bunch of numbers, and this relation holds. And that is simply, you will see that holds by just plugging in this formula for the Pijkl. So you should think of this as a kind of 2x2 determinant of some tensor of probabilities. But in general, there will be many more such polynomial relations among these probabilities Pijkl. And the question is, well, can you find all of them? And well, the answer to that question is yes, using Buchberger's algorithm. It's a form of implicitization. But now, what happens when some of these sets Ni become very big or even infinite? And that is what the theorem of is about. Namely, it says that if you take i's with I in an independent set and you let those tend to infinity, then the relations, the algebraic relations among the probabilities are in fact generated by finitely many sim n orbits of polynomials, and you can take these polynomials to have 2 terms like this polynomial that we have over here. So they are so-called binomials. And so an independent set is precisely what you mentioned before. It's an independent set in the underlying graph. So there must not be an edge between I and between the elements, between the i's for which you let the ni tend to infinity. Right. And the reason why that is and how it relates to this theorem over here is the following. Just in this case, for instance, if you let I and L tend to infinity, then in the parameters you see that there is an aij here and a cjkl and a bik here, and you see that in all of those parameters there's only one index that tends to that is allowed to be infinite. I mean, that's allowed to be unbounded. And so together these parameters correspond to finitely many rows on which the infinite symmetric group acts. So there's finitely many this number k is going to be the number of well, it's going to be something like the product of the nj where j does not lie in the independent set. So that's roughly speaking how they use this theorem due to Daniel Cohen to prove their independent set theorem. Okay. So that's one application. Now there are many more applications, but I wanted to let me keep an eye on the time. Yeah, there are many more applications, but I don't have the time to go into them. So let me instead try to advertise a new theorem due to Rob Egermond, Azar Farouk, and myself, which says the following: if you have a sim n preserved subvariety of c to the k times n, and you let xn be its projection in c to the k times little n, so you remember only the first n columns of this matrix and not the remaining ones, then xn, well, strictly speaking, maybe you should take the closure of the projection. That's going to be a variety sitting in c to the k times n, and the number of orbits of the symmetric group Sn on acting by permuting columns in this variety on irreducible components of this variety xn is going to be a quasi-polynomial in n for n sufficiently large. Now a quasi-polynomial it's like a polynomial, but the coefficients of the polynomial are themselves periodic functions of the number n. So instead of writing down a formal definition, let me just give an example of this. So suppose that k is just equal to 1. So we're looking at one infinite vector, and the variety we're looking at is defined by the equation saying that xi squared is equal to xj squared for all I and j. That is certainly something that is preserved by the infinite symmetric group. And now this equation is a product of two things, namely xi minus xj times xi plus xj. And on every irreducible component, one of these factors must be identically 0. So on a component of xn, you have that either xi is equal to xj on the entire component, or xi is equal to minus xj on the entire component. And then it's easy to see that these irreducible components then just correspond to unordered partitions of the set 1 up to n into two parts, into two sets. And in fact, one of them or both of them might be empty, or one of them might be empty. And so these partitions, these parts just say, well, these variables are equal and they are minus the other variables, which themselves are all equal. Okay. And well, if you look at the number of orbits of the symmetric group on this set of unordered partitions, then it turns out you can, well, let's see, you can take for A, well, you can first assume that A is at most as large as B, and then you can assume that the numbers 1 up to something are in A and the remaining elements are in B, and then you have a kind of normal form. And so the size of A is then, well, something running from 0 up to n divided by 2 rounded downwards. And you see this is a quasi-polynomial in n. This is a linear polynomial in n, which where the coefficient of n, no, probably the coefficient of n is always a half, but the constant coefficient is a periodic function that depends on the parity of n. So this is a quasi-polynomial in n. And so our theorem says that this is always the case, even for bigger k. Okay, this turns out to have quite interesting consequences in algebraic combinatorics. So here's one corollary of which I wouldn't have any idea how to prove it otherwise than using our theorem. Namely, suppose you take a finite set and you fix a number r, and you take for mn the set of all n by n matrices whose entries are in this finite set S, for instance 0 and 1, and you require that the rank of that matrix is equal to R. Okay, then it turns out that the number of orbits of the symmetric group, which for some reason this time I wrote as sym n instead of Sn, the number of orbits of the symmetric group acting by simultaneous row and column permutations on this set Mn is a quasi-polynomial in n for n sufficiently large. So already for n is equal to 2 and say S the set 0, 1, it's not completely not completely easy to actually find this quasi-polynomial, but for every R and S it is a quasi-polynomial. Right. Now, the bad news is that this is where it stops when you are interested only in the symmetric group. So there's no analog of Hilbert's basis theorem under the symmetric group. As soon as you have a matrix or a higher order tensor. So basically this is all we can say about this finitely many vectors is all we can say about symmetries where only the symmetric group acts. Okay, so this is the end of part 1. The next part will have to be significantly shorter, but maybe nevertheless, let me pause and ask if there are any questions about this.
Yes, I was a bit confused about the partitioning of n into 2 parts in the previous example. Would you please elaborate? Would you please elaborate? Yeah, in this one. So how did you get the partition of n into 2 sets, A and B?
Right. So when you take a component of xn, then on that component you have equations saying things like x1 is equal to x2, and then you put 1 and 2 in the same partition. And for instance, x2 is equal to minus x3, and then you put x3 in the other part of the partition. And so you do this for the entire, for all the equations that you get on this fixed component, and that gives you such an unordered partition. Does that make sense?
Got it. And why did you say unordered?
Yeah, that's a good question. So somehow, how should I say this? If you swap A and B, you still have the same component. That's what I want to say. So by unordered, I mean that if you replace A by B and B by A, you're still describing the same irreducible component.
Okay. Thank you.
Okay, you're welcome.
And John, does this particular result of yours and others, does this have the same implication in the other operators like inc operator, what Tim Romer and other persons were doing?
Well, it's a good question. You see here, we really need somehow invertible symmetries, and we prove our result using actions of not only groups but also finite groupoids on some sets, on some rational polyhedra, in fact. And I don't know if there's an analog of this for just varieties that are only preserved under increasing maps. No, I don't know that. I wouldn't know a guess even how to formulate it, and let alone that I would know that it is true.
Okay, thank you.
Okay, you're welcome. Okay, so let me just briefly say a little bit in part 2. So now we have tensor tuples under GLN, and so we have GLN acting on a space of which I call TT, which is the space of all tensor tuples consisting of n0 numbers, n1 vectors, and 2 matrices, and so on until nd dimensional tensors. And then, of course, so this is the geometry, so to say. And then it also acts on the ring of polynomials in the corresponding coordinates on those spaces. So the coordinates are x, e, j, I1 up to IE, where e runs through 0 up to d. So it just specifies what type of tensor you're looking at. J runs through 1 up to NE, which just says which of the tensors of that type you're looking at. And then I1 up to IE are just the indices of that tensor. And GLN acts on that space. And then, well, a fundamental result is that, that in fact, every GLN preserved subvariety of this rather complicated space TT is defined by finitely many GLN orbits of equations. And so there's no restriction on the type of tensors or so here. So this is, from that perspective, the situation is much more satisfactory than in the case of the symmetric group, where we were forced to restrict ourselves to just finitely many vectors. So let me just give you a feeling for what kind of varieties these are. For instance, if you look at the rank at most K matrices in C to the n times n, well, they are defined by the vanishing of all the K plus 1 times K plus 1 subdeterminants, and turns out they are contained in the span of a single GLN orbit of equations. And well, here's another example, slightly more complicated. If you're interested in tensors, three-way tensors that are of the following form, you take a slice in this direction, say, and you take scalar multiples of it back and forth, plus a slice in this direction and scalar multiples of it back and forth. Those tensors are said to have slice rank 2, and they are defined by the GLN orbit of a single cubic equation and a certain sextic polynomial, which is an interesting polynomial arising as a 2 by 2 determinant of a matrix whose entries are 3 by 3 determinants. And okay, so these are just two examples, and I want to mention for applications this might be useful, this theorem, because so if you want to test whether the rank of a matrix is at most K, then one way you could do that, which is not the standard way, is that you just left multiply it with a random matrix and you right multiply it with the same random matrix, or no, let's say with the transpose to stay in the right setting. And then you look in the upper left K plus 1 times K plus 1 matrix. And if the matrix that you see there has 0 determinant, then with very high probability, the matrix that you started with has rank less than or equal to K. And so this type of algorithm, say a randomized algorithm for testing whether the rank is at most K, actually exists for every GL capital N preserved subvariety of TT.
Just one question regarding to the previous figure. Are there any connection of these varieties with Draisma?
I'm sorry, I must admit I didn't get the question, sorry.
In the previous slide.
On the previous slide, yeah.
These kind of varieties which are being discussed in the theorem, do they have any connection with Grassmannians?
Do they have connections to Grassmannians? Yeah, so that's right. So in particular, well, this theorem, for instance, would say things like, if you are interested in the, well, let me try to be careful here. If you're interested in the Grassmannian of k-dimensional subspaces of a vector space V, where k is fixed but V is not fixed, or V can be even infinite dimensional, then such a Grassmannian is defined by finitely many orbits of equations. In fact, in this case, one orbit suffices. And the same holds when you replace k by when you replace the Grassmannian, for instance, by secant varieties of Grassmannians. Now there's a version of this theorem for Grassmannians and related varieties where not only the dimension of the underlying vector space is allowed to become infinite, but also the order of the tensor is allowed to change. So that's more complicated and not strictly covered by this theorem.
Thank you very much. Thank you.
So in continuation of Imran's question, Jan,
Yeah.
is there a concept of Borel subgroup and things like this in this, or a parabolic subgroup, or not yet?
Yeah, so, well, I mean, let me see. So this GLN has an obvious Borel subgroup, right? It's just out of triangular matrices. And I think it is correct that to study these ideals, you could study them by looking at the, looking first at the highest weight vectors in the ideal and so on. I don't think people have done this very much yet. And in particular, it would be very interesting if there were a kind of Grosvenor basis type approach where somehow a Grosvenor basis consists of highest weight vector. So I don't know how to make this precise yet, but it would be great if there were a kind of Buchberger algorithm here having to do with the Borel with highest weight vectors, but we don't know how to do that yet.
Okay, thank you.
Okay, thanks. Okay, so I think I'm slowly running out of time. So let me just very briefly say there's a version of Chevalet's theorem here. The image of a GLN equivariant polynomial map is always constructible. And I had an example here, but maybe I'll skip the example and continue to the last slide. So there's a lot of other things. Like, for instance, there's a theorem that says the following: if you take a point in this TT and you take its orbit under the infinite GLN, then there are only two possibilities. Either it is the entire space. Well, okay, you need to take the closure of the orbit. Either it is the entire space, or it lies in the image of a smaller space of tensor tuples by means of a GLN equivariant polynomial map. So that's a very strong result. So either your tensor is as complicated as it can get and its orbit is everything, or it is not complicated because you can describe it by means of a smaller tuple of tensors. Right. Well, there's a very beautiful universality result due to Kastan and Ziegler, which if someone wants to know, I can tell something about later. But let me just conclude with two things, namely, first of all, a slogan, which is that, most theorems in finite dimensional affine varieties have analogues over GLN, as opposed to the infinite symmetric group, where we were, very much restricted to this finitely many vectors case. However, there are many open problems yet, and I wanted to mention two of them. First of all, the theorem that I mentioned, that I proved some years ago about a kind of finiteness result, is not really Hilbert's theorem, because it only says that a variety is defined by finitely many orbits of equations as a set. And that means that every GLN stable ideal is the radical of some ideal that is generated by finitely many GLN orbits of polynomials, but we don't know that it is itself actually generated by finitely many GLN orbits. That's almost completely open, except in very small cases. And then there's a computational open problem, which is that is there an algorithm that takes as input finitely many polynomials, f1 up to fn in the coordinate ring CTT, and that decides whether the variety defined by the union of their orbits, so every element of the form G times Fi, where G is in GLN and I runs from 1 to n should be equal to 0, whether the variety defined by that union is irreducible. We don't know whether this is decidable even or not. And so if it were decidable, then there would also be a version of, say, Buchberger's algorithm, which allows for implicitization, which allows for computing the images of the equations defining the image of a polynomial map. But we're not nearly there yet. Okay, so I started by giving some, recap of very traditional finite dimensional algebraic geometry, and I hope to have given you a flavor of what sort of things, Hilbert's theorem, Buchberger, and Chevalley, we can generalize to the infinite dimensional setting in the presence of a lot of symmetry, but there's a lot of work to be done yet. And so if anyone is interested in joining this effort, they are more than welcome. Thank you.
Thank you very much.
Thank you very much. Yes,
So,
yes.
so just one question. So you mean there's something like Noether normalization also in this context or not?
It's a good question. So we don't have a precise version of that. No. So that, and I wouldn't know exactly what the right statement is. But let me say something. What often happens both in this GLN setting and in the SimN setting is that if you start with your variety and you do a kind of shift, and in the GLN setting and also in the SimN setting, this just means that, so to say, you move the first, say, 100 dimensions into, you sort of fix those, and you act. Okay, let me say it differently. So in the GLN setting, you can take your group, GL infinity, but take the subgroup that fixes, that is the identity on the first 100 dimensions, say. And then the group that remains is still isomorphic to GL infinity, and the space that remains is still isomorphic to a bigger space of tensors on which this new GL infinity acts. And after such an operation, followed by a localization, many things become nice. So for instance, every such variety becomes of the form a finite dimensional variety times a space of the shape dt. And so, yeah.
And if, I mean, naively, if one takes Cx1, the ring, x1, xn, and so on, and one tries to do algebraic geometry as one does for when n is finite, I mean, is that too wild a thing, or?
Well, yeah, of course you can do it, but if there, so you mean if there's no symmetry at all? Yes. Yeah, of course you can do it, but very quickly, if you're application minded, then you would like these varieties to be described in some finite way, right? And,
yes.
And so, well, yeah, if you only write down finitely many polynomials, well, then of course the remaining variables are not used at all. So you could as well leave.
Yes.
Yeah, I don't know. So.
Yeah. Okay. Thank you.
You're welcome.
Any other question from the audience? Okay. In fact, we already asked many questions during the talk, and John, it was a wonderful talk. And I would say it was a very, very fresh talk, because I think the paper appeared like 2 weeks ago, I think so, on Archive.
That's right. The paper with Rob and Azar appeared a few weeks ago on the archive. That's right. Yeah.
Archive. And definitely these new structures are very enticing, and a lot of work is being done in this direction. And I really appreciate your efforts in trying to answer every question with the limitation of online talk. And this is always a difficult thing, and we have the facility of the board, then the things are much more easier. And the discussion, I hope the discussion would continue even after the tea, if we would have you physically here. But anyways, I hope everyone had a good time attending your talk, and you presented in a very, very nice way, and you answered every question quite clearly. Hania, you have some questions? Okay, Hania, go ahead.
Sorry, so for people who are seeing these things for the first time, that would be me. Just to know what do you mean by applications, because it seems that most of this is application driven. So it wasn't a question. It wasn't a natural like generalization or something that was finite dimensional. Like, what would it look like in infinite dimensional? But it seems to be the other way around, like driven by application. What kind of applications are you looking at?
Right. So in view of time, one important aspect of this that I didn't describe very well, or not at all, in fact, is that so what you often have is things like this. So for instance, you have some statistical model, and you have a which involves a number of random variables. And for instance, either the number of random variables becomes larger and larger, or the number of random variables is fixed, and the numbers of values that they can take becomes larger and larger. And then very often in these settings, it turns out that you can take a kind of projective limit of these models, and that is such a variety of tensors that I described, on which either the symmetric group acts, for instance, by permuting random variables, or also a group of linear transformations like this GL infinity acts. And so this is a way of sort of finding algebraic descriptions of all of these models at once by finding them for the projective limit. And so one example that I gave of this is this independent set theorem, but there are more. For instance, there's a model in statistics called the Gaussian K-factor model. It's in Gaussian factor analysis, where the matrices, the covariance matrices, are of the form a positive semi-definite rank K matrix plus a positive definite diagonal matrix. And then the question is, if the matrix is very large, how do you recognize whether it is of this form? And it turns out there's a very nice theorem by Matthias Durton and a collaborator that says that, for instance, when K is equal to 2, if I'm not mistaken, so when the number of factors is equal to 2, then you can recognize such a huge matrix by looking at only 6 by 6 principal submatrices. And so you should think of our work as a kind of analog of this. So you can recognize points in these very large dimensional algebraic varieties corresponding to statistical models by looking at certain, at many but small blocks of the structure. So that's roughly where our inspiration comes from.
Right. Thank you so much.
Yes, Anish.
Yes, I just wanted to continue from Hania's question of applications. Of course, it has applications in, I suppose you also told about us an algorithm of matrices, which is a randomized algorithm, and to compute the rank of the matrix of the matrix it gives us a lot of solutions in some bounds in combinatorics. For example, in graph theory, Hamer's bound, it's bounded by it bounds the Shannon capacity by, for example, by the rank. So it gives a lot of applications in information theory and combinatorics as well, which I'd like. Of course, in simplical complexes, it might also be applicable in other fields such as TDA.
Okay, thanks for the comment. Yeah, in connection to graph theory, I wanted to mention that there's very nice work by David Spire and okay, the name of his collaborator escapes me for for the moment. So David Speyer and someone else, they study graphs that depend that depend on the functorially on the choice of a finite set, so-called FI graphs, and so they ask questions like, how does the spectrum of such a graph behave when the number of when the underlying finite set becomes bigger and bigger, and so that goes a little bit in the direction that you mentioned, I think.
Any other questions left or any comment? Okay, if this is the case, let us thank the speaker once again. Thank you, Professor Draisma, for a very nice talk. And one announcement for all the participants. Those participants who are interested to have a recorded video of this talk, they can send an email to events@langs.edu.pk. So in reply to that email, we will send you the Google share link of a recording of this talk. We will send it to you as well, Charisma, if you need
Okay,
it.
great.
Okay, thank you, everyone. Thank you for. Bye bye. Take care.
Thanks. Bye bye.